Hey guys, welcome back to another one of Dr. Monroe's material science videos. In this video, we're going to be discussing crystal math and crystallography. I'm going to give you a couple of examples to try to clarify what we went over last class period. So in crystal math, we talked about vectors and we talked about planes. For crystal vectors, what we learned was that the vector was normalized relative to the crystal itself. And so I'm going to give you an example of kind of the differences and similarities across different crystal types. So if we have two crystals, so one of them is cubic, this is the one on the right, and the other one is orthorhombic, this one on the left. If we have a vector that is the same in both crystals, and looks like this. It goes from the origin to that distance right there. Those vectors are exactly the same in real space. They point in the same exact direction. But in relation to the crystal, they point in different directions, and we'll see what we mean by that. So this crystal to the left, let's say, for instance, this is the C edge. Let's say the C is equal to 2 angstroms, which is, the distance of each one of these little marks. This distance right here, which would be B, is equal to 4 angstroms. And this distance right here, A, is equal to 3 angstroms. And this is just a hypothetical crystal. This crystal on the right, the C-axis, is equal to only 2 angstroms. The A-axis or the B-axis rather, is equal to 2 angstroms. And this A-axis is equal to 2 angstroms. So for a cube, we actually say that the unit cell edge length is only A, and A is equal to 1 number. So when we start trying to describe this vector, we can break it into components in the different directions. So this orthorhombic one, the component in the x direction is that long, and the way we describe this is we say that that distance would be 1 angstrom, and in relation to the side A, it is equal to 1/3 of the side A. And then we can do that the same thing with the z component. The z component, we can see that this vector, this component of that vector, is 2 angstroms, and if we compare it to the side C, we'd see that it is 1 times that side C. So now let's turn our attention to the other vector, or the vector in the cubic system. So the component in the x direction for this one is going to be equal to 1 angstrom. But unlike the orthorhombic crystal, this is equal to 1/2 of A, not 1/3 of A. And this component in the z direction is equal to 2 angstroms. And that is equal to 1 times C. Okay? And to distinguish between the two, I'm going to say this is C prime, B prime, and A prime, just to show you that it's in the cubic crystal system. So now we have the projections on the different axes. And you'll notice on both of them, the vector has no projection along y, so therefore it is 0 for both. So if we start to follow the list of kind of procedural list to determine what vectors these are, the next step is to read off those projections. So the projection in the x, y, and z is along x would be 1/3 the unit cell in that direction. Y would be 0, and z would be 1 full length in that unit cell direction. And we need to find a common factor, and so we need to multiply by 3. So it would be 1, 0, 3. And then we put it in square brackets. And so for this vector in the orthorhombic crystal system, it is 1, 0, 3. That's the description of that vector. Now, if we look on this other side, on the cubic system, x prime, y prime, and z prime, what we'd see is that in the x direction, instead of going 1/3 of the unit cell length in that direction, we only go 1/2. In y prime, there's no component, and therefore it's 0. And z is the same as in the orthorhombic, or the c-axis is the same, and therefore it's 1 unit cell edge length in the z direction. And so again, we have to find a common factor, and so this would turn into 1, 0, 2. If we put it into square brackets, this would be the vector that describes, this would be the number that describes this vector in the cubic system. So now we have something that's very interesting. We have two vectors, and they point in exactly the same direction in Cartesian space, in a Cartesian coordinate system. But if we take that the vectors and put them into the relative crystal coordinate system, they will be different. So that we're going to do something very similar, and we're going to look at planes. So we're going to see how the different crystal systems will affect different planes. So if I told you that I want you to draw the 1, 1, 1 plane in the orthorhombic system and the cubic system, what we'd do is we'd follow the procedure for determining plane normals, because remember, this 1, 1, 1 plane is the normal to that plane. That vector is the normal to that plane. And if we were to start drawing it, we'd follow the reverse order of the list of the procedure. And so that procedure tells us, okay, we need to take the inverse and all that other stuff. This is fairly simple to do, and we can easily show, or easily see, that in the orthorhombic system it will intersect the x-axis at 1, it'll intersect the y-axis at 1, and the z-axis at 1. Now remember, this is 1 unit cell edge length, very similar to the vectors. It's not 1 angstrom, it's a 1 unit cell edge length. And therefore, the plane, the 1, 1, 1 plane in the orthorhombic system will look like this. Now if we drew the 1, 1, 1 plane in the cubic system, it will intersect the x-axis at 1 unit cell distance, the y-axis at 1 unit cell distance, and the z-axis at 1 unit cell distance. And so if we draw the plane for this 1, 1, 1 normal vector, we'd see that it's this plane right here. And to kind of show you, if we take this blue plane and kind of superimpose it onto here, it would go between here, here, and here. So even though we have the same math, it's the 1, 1, 1 plane in both crystal systems, because they are different, because the edges of the unit cell are different, they will actually have different normal vectors if we look at it in a Cartesian coordinate system. But in the crystal system, those vectors are exactly the same.